Hello students, today we are going to discuss about the important aspects of electric field. In the last video we have studied about what is electric field and unit of electric field. So we have derived the expression for electric field. E vector is equal to 1 by 4 pi epsilon naught q by r square into r cap, and unit of electric field is Newton per Coulomb. Okay. Now we are going to discuss important aspects of electric field. So simply we can define the electric field. E vector is equal force experienced per unit charge. The first point, if the charge is plus q, the electric field, it acts radially outwards. It means the direction of the electric field point away from the charge. If the charge is negative, minus q, then the electric field is acting towards the charge. The direction of the electric field acting towards the charge. It means it points towards. Okay. This is the first point, first aspect. And then second one, if the electric field at a point P is E, then for example at a point P the electric field is E. The force experienced by the test charge, this is called source charge. Here the charge at the point P is called test charge. Okay. The electric field at the point P is E. The force experienced by the test charge is F vector is equal to E vector into Q naught. From this equation we can write, just rearrange the expression for F vector, where F vector is equal to E vector into Q naught. Here there is a Coulomb force in terms of electric field. This expression represents the Coulomb force in terms of electric field. Next, third point, the equation E vector is equal to 1 by 4 pi epsilon naught q by r square into r cap. It means the electric field, it is independent of the test charge. The electric field is independent. See the equation. In this equation there is no q naught. It means there is no test charge. There is only source charge. So the electric field is independent of test charge and it is depends source charge. Next, the fourth point, the electric field is a vector quantity. At every point in space, the electric field has a unique direction and magnitude. Unique means it's a different direction and different magnitude. Let's see it in the diagram. Here at the point P, the P is very close to the charge plus Q, so that the magnitude of the field is large, so that the length of the E vector is large. And here the direction of the electric field, in this direction, here the direction of electric field is different from the first one. Here the direction of electric field is different from others. So at every point the direction of the electric field changes. Similarly, the magnitude of the electric field at the point P, it has a large magnitude. At the point Q, the magnitude of the electric field is very less, because the point Q, it is far away from the plus Q. When the distance increases, the electric field will decrease. So from this equation we can understand this, because the electric field is inversely proportional to square of the distance. Next, fourth one, it is assumed that the test charge, it is very smaller than source charge. Here I have assumed the test charge is very small. Why should I assume like that? Because the test charge, it should not alter the electric field of the source charge, so that I assume the test charge is very small compared to the source charge. The electric field E vector, it is valid only for point charges. Point charges means it is considered to object. The object, it contains charge. Here they are separated by a distance. If the size of the object is very small compared to the distance between the two objects, then the charge material or charged object can be considered as a point charge. So here the electric field equation is valid only for point charges. For finite sized uniform distributed charges, we have to use integration techniques. That we will see later. Okay. This equation also gives an approximation for finite sized charge distribution. For example, if the test charge Q0 and there is a source charge Q, if they are separated far away, if the test charge is separated far away from the source charge, then we can use this expression for an approximation. We can get approximated value of electric field by considering these two objects as point charge. Because the same phenomenon we are using in gravitation, similarly we will treat the earth as a point mass while calculating the gravitational field of sun on earth. Because the distance between the sun and earth is very large compared to their size. The seventh aspect, there are two types of electric field. One is uniform electric field, and the second one is non-uniform electric field. Okay. What is uniform electric field? If we calculate the electric field at any point in space, the direction and magnitude, for example, this is the length of the vector represents magnitude and the arrow mark represents direction. At every point, the direction and magnitude of the field is same, then it is called uniform magnetic field. Suppose if the direction and the magnitude of the electric field changes, then it is called non-uniform electric field. Let us consider an isolated positive charge. In this case, the electric field radially points. It means the direction of the electric field pointing radially outwards. Here, very close to the positive charge, the electric field is very large. Very close to the electric charge, the electric field is very large. When you move far away from positive charge, then the magnitude of the electric field will decrease. So this is an example for non-uniform electric. Next, electric field due to system of electric charge. System of electric charge, it means electric field at a point P due to more than one charge. If there is more than one charges, or if there is n number of charges in a material or in an object, then what is the electric field at the point P? This we can determine by using superposition principle. So already we know that what is superposition principle. So E vector, E total, it is total electric field at the point P. It is equal to vector sum of the electric field due to individual charges. Here, so electric field due to the charge Q1, electric field due to the charge Q2, and electric field charge, so electric field due to the charge Q3. That is E1 vector plus E2 vector plus E3 vector up to, we can write En. Suppose if the system has n number of charged particles, we can write the total electric field. Okay. Here, We know the general expression for electric field. E vector is equal to 1 by 4 pi epsilon naught q by r square into r cap. In this case, we can write the E1, E2 and E3 up to En, where E1 is the electric field at the point P due to the charge Q1. For example, let's write E1 is equal to 1 by 4 pi epsilon naught, where the charge is Q1. So Q1 by R1 to P. So that's why I'm using R1P. Similarly, the unit vector also acts along the same direction, R1P cap. So you can write the expression for other charges, that is for Q2, Q3. Just we have to change the value of Q2 and the distance R1P. Here the distance for the first charge is R1P. Here the distance between the point P and Q2 is R2P. Here the distance between the charge Q3 and point P is R3P. Okay. Now I'm going to substitute the value of E1, E2, E3 up to En. So E total vector, it is equal to, we know that E1 is equal to 1 by 4 pi epsilon naught. Similarly, 1 by 4 pi epsilon naught, it will be common in all the equation E1, E2, E3 up to En. In all the equation, the value 1 by 4 pi epsilon naught is common. So I'm going to write it as common 1 by 4 pi epsilon naught. The electric field due to the first charge Q1 is Q1 by R1P square into R1P cap. Similarly, we can write for the second charge Q2 by R2P square and R2P cap. We can write up to nth particle, nth charge particle. So Qn by RNP, Qn by R, yes, it's NP square RNP cap. So this equation, it's very length, the length of the equation is very large, so that I'm going to write it in a short form using summation. E total is equal to 1 by 4 pi epsilon naught. I'm going to use summation symbol. So instead of Q, I'm going to use symbol Qi by RIP square RIP cap. Here the value of the I is equal to 1 to N. So this is a short form of writing total electric field. In this case, the magnitude of the electric field is distance between the point and electric charge. Here the Q1 charge Q1 is very close to the point P, so that the electric field, the magnitude of the electric field is very large. In this case, the Q2 charge is far away from the point P, so that the electric field is very small. That's why the magnitude of the electric field is very small. So the electric field, magnitude of the electric field depends distance between the point and the charge.